Okay, we're up. Can start.
Okay, thank you once again for for joining us. Today we have Alexander Wilson, and the title of his talk is Real Non-Patterns in the Automation of Science. And before I introduce him properly, I'm just going to say a few words about the school from Materialist Research: contemporary science, philosophy, art, mathematics, design, architecture, and politics. SMR is an international platform founded by the Center for Philosophical Technologies at Arizona State University, the Institute of Social Sciences and Humanities, Skopje, the Department of Architecture, Theory and Philosophy of Technics at the Technical University of Vienna, and the Critical Inquiry Lab at Design Academy Eindhoven. SMR functions as a global online school combining education, research, and mentorship to advance academic study at the intersection of the social sciences, humanities, and STEM sciences. And the spring and summer sessions are offered for free and open to the public, serving as promotional events that illustrate the programmatic commitment and style of work offered by the School for Materialist Research. And without further ado, I'd like to introduce Alexander Wilson. It's a great pleasure to have him here. He writes about the perceptorium.
And that containers cannot contain everything, including themselves. I was reading Maria Puig de la Bella Casa recently in her book, Matters of Care. And in the second chapter, you find an interesting account of a shift in approaches in STS following the development of thought in Donna Haraway and Bruno Latour and others. There's been a softening of critique. As the young critics become more mature, they become more careful about their attacks on the scientific status quo. Latour sees his perspective changing after the science wars, finding that the discipline he helped found had overrun even the limits he had helped displace. Critique ran out of steam because it was not being careful, because it was getting tricked by matters of fact, making us take them too seriously. His deployment of the concept of matters of concern, a category more general and polymorphous, more virtual than the actual matter of fact, was no doubt a strategy of de-escalation. He reminds his fellow science students that the goal is not to debunk, to crack open, to dismantle, etc., to show the falseness of some position or its double standard. The question, this is a quote by Latour, the question was never to get away from facts, but closer to them, not fighting empiricism, but on the contrary, renewing empiricism. He promotes a stubbornly realist attitude, argues that critique has not been critical enough. It lacked nuance and rigor. It was too blunt, throwing the science babies away with the capitalism bathwaters. Latour saw this 20 years ago. In 2016, at the height of the popularity of the post-truth buzzword, Latour found himself again having to defend science and to nuance his reputation as a critic of the institutions and so-called methods of science. It's easy to criticize, but care, as Puig de la Bella Casa reminds us, care is also about being careful about critique, careful thinking. So it's also with an eye to these developments, these readjustments of thought in the humanities as it recovers from post-structuralism, that I would like to discuss a most interesting return of structuralism in contemporary philosophy of science, and indeed within science itself. James Ladyman and Don Ross's incredible work in Everything Must Go, a book from 2008, written in collaboration with John Collier and David Spurrett. So this is a collectively written book. The book needs to be recognized as an important, patient, if polemical, contribution to this field, a careful thinking about science and its relation to philosophy. It actually campaigns for a full-blown return to structuralism, but it is different from the 20th century structuralism, the mid-century structuralisms. And I would like to, in this talk, to investigate some of the points of connection and some of the points of divergence. In any case, the book is a commendable work of collectively written nuancism, an application of nuance and rigor within a field that is often too quick to take sides, quick to take sides, as well as an attempt to really accommodate really the least intuitive scientific discoveries of the physics of the last century. What scientific discoveries am I talking about? General relativity, Einstein's hesitations with the arbitrariness of choosing a particular coordinate system in his general covariant field equations led to what he considered the most significant of his discoveries. What he discovered at the end of this long struggle with the meaning of the coordinates is that there's no such thing on the fundamental level of description as points in space-time. There are only space-time coincidences. Points in space-time do not pre-exist the determination of material coincidences. The notion of a background independent of this determination has no meaning. If Newtonian physics had reified a substance of space and a substance of time, time just keeps ticking along at the same rate in Newton, and space is just there empty, waiting for things to fill it up. The picture after Einstein does not allow this idea. What it amounts to, what general relativity amounts to after this, the whole argument that led him there, is that if there is no fact of the matter about space-time coordinates beyond specified space-time coincidences, then it is, in a sense, we as observers who determine through acts of measurement, by glancing at a clock, for example, and seeing that at time t, the minute's hand is pointing in one direction or another, a coincidence is space-time. We fix a space-time, a material coincidence by doing that. So even before getting into the quantum entanglement and all that weirdness, it seems that any measurement determines the shape of space and time, for there is no background to the act of observation. Space and time are, in a sense, secreted from the act of fixing some simultaneity, some frame of reference. But there's thus no background to this operation of coincidentalization to which corresponds all observation. Thus, space-time should be seen as an emergent effect of the interaction between dynamical systems rather than a context or container for such interactions. As Carlo Rovelli puts it, there are no longer any fields on space-time, just fields on fields. So, of course, the other big 20th century discovery we're talking about here is quantum mechanics. As everyone knows, it will have further threatened our traditional notions of determinism, the kind of causality we have evolved to be familiar with, the classical billiard ball causality, where a historical account can be given of an order or sequence of events following a chain of causes and effects, is not specified at the quantum level of description. The violation of the Bell inequality seems to make it ever more unlikely that anything like that kind of determinism holds. This remarkable result seems to prove that quantum physics is not just an effect of our ignorance, or at least not our ignorance of hidden variables, because no such traditional billiard ball type variables, in other words, that obey the constraint of locality, that are here or there rather than here and there, no such variables could ever produce the observed quantum phenomena. Another salient example from quantum physics, the quantum eraser, which has been discussed by Karen Barad to great effect, and in particular, the delayed choice quantum eraser experiment shows that, strictly speaking, the past itself it can be erased and rewritten even after it has been established as a past. It seems that there can be no fact of the matter about any historical succession of events or about the singular forward-moving flow of time humans have since perhaps the dawn of writing assumed to be fundamental. Throughout the 20th century, of course, we have figures in the humanities who want to defend ideas of time, durée, process, and becoming from the apparent encroachment of these, lifeless structures being discovered behind appearances. Of course, we have Bergson quite prominently rejecting Einstein's theory. Because it seemed to, in his view, render impossible what we all intuitively know to be true, the forward movement of time. Life as flux, it withers away, it approaches in phases. It's never given all at once. And essentially all spatialized time is no longer time. Any geometrical fixation of time lacks the fleetingness of time as lived. Therefore, all models, all scientific models are ultimately wrong. There was a resurgence of this kind of thinking, though with a more scientific clothing, in the mid-century, with the increased study of nonlinear processes, chaos theory, far from equilibrium thermodynamics. We have Prigogine, for instance, who will say, it is only when systems are at equilibrium that they look static. When they're far from equilibrium, they're directed, they're asymmetric, they're dynamic. They're attracted to various attractors, and they diffuse into various phase spaces. And those phase spaces are, ultimately open. The whole universe is an open space. He speculates. So instead, where in a closed space, the phase space will determine the future of the system. In an open space, there's no such determination. So, they'll say, these people will say, the story is not written in stone, and they'll celebrate this kind of idea of, there's infinite creativity of nature. Prigogine will argue that we've overprivileged equilibrium. The development, this stems from the development of industry, steam power and internal combustion engines in the 19th century. Of course, will have led us to discover entropy and the second law of thermodynamics, this apparent arrow of time, which for a while there did seem like it was fundamental. But after having absorbed the meaning of the results of quantum and relativistic physics, it seems fairly obvious that Sir Arthur Eddington was wrong. We can no longer say that the law that entropy always increases holds the supreme position among the laws of nature. The whole question of emergence is also on similar terrain. Emergent properties, irreducible behaviors, how different qualities emerge when quantities change, how more is different. The whole question of complexity sciences, the Santa Fe Institute, for instance, is concerned with studying such phenomena, power laws, emergent top-down effects of large complex systems. But this terrain is also forced to face a similar kind of dilemma. Is emergent complexity really a feature of the real, or is this an effect of observer ignorance, a kind of emergent effect of our observation? The connection of thermodynamics with information theory highlights this aspect. The Shannon's equations describe communication systems as much as thermodynamic systems. Let this loud ambulance go through. So Shannon's equations, because in fact, entropy is a measure of noise in the signal as much as, entropy is scrambled information that we have trouble tracking, information that's difficult to track, to descramble, to unscramble. So really, none of these theories of emergence really stand up to the more fundamental physics of near and far, and what these physics have told us now in the last century about causality and determinism. The idea that there are no objects in the world, and that these, this idea that there are objects in the world that bang into each other, and that produce, equal and opposite reactions to each other. That picture is probably wrong. And the idea that the world is made up of small things that microbang each other, atomism, the whole logic of Mariology that accounts for our intuition for emergence, that large things are made up of small things, part-whole relations, that is also probably wrong, according to the picture given here. Perhaps causality was just an extra constraint that humans had evolved to impose on their surroundings from an evolutionary standpoint. And here the logician Julia Pearl, his so-called do calculus, I think, has compellingly suggested that causality is just such an effect. It is just the question of what happens when one intervenes, when one acts on the scene and collapses the probabilities onto a known certainty. In the same way that you fix something by glancing at a clock, you fix the coordinates. To demand causality is to do something and thereby know one of the causes in the system. You have prior information. So as soon as you do something on the system, you immediately orient the graph and you introduce acyclicality into the world. And that actually is the difference between correlation, where the arrows of influence go in every direction, backwards and forward through feedback loops and so on, and causation, where the arrows need to be directed. The structure needs to be ordered. It needs to have an order of priority such that one thing follows another. The arrows must go from the initial to the terminal object, through a series of causes and effects. The discoveries in physics seem to agree that causation as we know it, where the arrows of time, the arrows of time go in one direction, is not fundamental. And indeed, this is now being reflected in contemporary scientific practice. I mentioned in the abstract, this idea of the automation of science, but I would like us to keep this in mind, even though we won't be discussing, that much of it. It's kind of the point of this whole talk is really to investigate those things, although we won't get into the nitty-gritty details of what these AI systems are doing. But the automation of science, in a famous Wired article from 2008, The End of Theory, Chris Anderson, the editor of Wired magazine, predicted what we now see happening more and more in science. The argument is that the brute force analysis of increasingly large data sets overcomes the relevance of scientific method or the need for causal explanations of things. It becomes again possible to think of the computer as an oracle, progressively illuminating a higher and higher resolution picture of the real. No longer do we need to account for why or how. No longer do we need to reduce the event to a story with a beginning, middle, and an end. Neither do we any longer demand that there be a description of the scene or the context. Recently, Professor Hong Chin, who trains machine learning models on physical data with the purpose of training them for theorem discovery. He put it this way, I think he's at Princeton. I might be wrong about that. But. So he says, what I'm doing is replacing the traditional scientific process with a type of black box that can produce accurate predictions without using a traditional theory or law. Another example is Udrescu and Tegmark's AI Fineman, meant to automate the human physicist's general tool set of pattern recognition strategies. Indeed, if the goal of science is just to make better and better predictions, theories start seeming redundant. Everything might reduce to Bayes' theorem. With enough data, correlation trumps causation. Why should science waste time making itself digestible to human minds in the form of theories, narratives, visualizations, when it could just mechanically go from the data to the prediction? It's an interesting shift in science, and I believe it deserves to be contextualized within the last century of philosophy of science and mathematics, as well as to evolving notions of realism. In particular, we'll be looking here at structuralism and post-structuralism. So why structures? John Worrell, in his 1989 article, Structural Realism, The Best of Both Worlds, cites Henri Poincaré that we cited at the beginning, and his idea of the bankruptcy of science, but he also cites an overlooked kind of solution to bankruptcy of science that's in the same text. So by now, the problem is known as, in the 80s, it's known as pessimistic induction. But in 1905, Poincaré was giving an example of the transition from Fresnel's theory of optics to Maxwell's. If Maxwell's, so this is a quote by Poincaré, just a few paragraphs down from the initial quotation. If Maxwell's theory is preferred today, does it mean that Fresnel's work was in vain? No, for Fresnel's object was not to know whether there really is an ether, if it is or not formed of atoms, if these atoms really move in this way or that way. His object was to predict optical phenomena. This Fresnel's theory enables us to do today, in 1905, as well as it did before Maxwell's time. The differential equations are always true. They may always be integrated by the same methods, and the results of this integration still preserve their value. Importantly, Worrall underscores that Poincaré does not mean this in an instrumental manner. He does not mean to say that science only specifies predictions about what will happen when one sets up an experiment in this way or that way. So I continue, Poincaré. It cannot be said that this is reducing physical theories to simple practical recipes. These equations express relations, and if the equations remain true, it is because the relations preserve their reality. They teach us now, as they did then, that there is such and such a relation between this and that thing. Only something which we call motion, we now call electric current. But these are merely names of the images we substituted for the real objects, which nature will always hide from our eyes, or which nature will hide forever from our eyes. The true relations between these real objects are the only reality we can attain. So Poincaré suggests that equations, relations, patterns, or structures carry over from one theory to another. They survive the paradigm change of a scientific revolution. And Worrall, in the 1980s, revives this argument, saying it provides the best of both worlds. We can, without science being a miracle, we can still not be too pessimistic about its progress. Ladyman and Ross agree with the general line of thought here in Everything Must Go, more recently in 2008, 2007. Ladyman and Ross agree with that general line of thought, but say we should go further. In Poincaré, as in Worrall, there's still a sense that these relations are the best we can do, given the circumstances. Nature will forever hide the objects. The noumenon is forever hidden from scientific inquiry, but at least we can study the relations between those objects. Ladyman and Ross will argue that no, it is not that such structures only give us epistemic access to the real, but that these structures actually are real. They are not just relations between noumenal objects. There is no longer any real behind the relations. All there is in the real are such relations. And so the structures describing such relations are the real itself. There's nothing behind them, as it were. Another influence in Everything Must Go is definitely the causal or physical theory of reference after Putnam and Kripke and others. Ladyman and Ross build on this. They extend some of these ideas from the causal theories of reference. Roughly, very roughly, it's based on the idea that one cannot refer to something that isn't somehow there. Putnam famously puts it this way: we're not living in a simulation. I am not a brain in a vat, because because the statement, I am a brain in a vat, is false whether or not I am a brain in a vat. The argument is an absolute dismissal of skeptical arguments, where doubt itself seems to be caught in the midst of a performative contradiction. Descartes' I think, therefore I am is replaced with I refer, therefore there is a referent. We are, in a sense, forced to comply with our own references to the real. We're not at liberty to decide. We're stuck with them and stuck in them. So in this paradigm, the descriptions vary from world to world, but the references remain fixed for all possible worlds. This is an important part that it comes from Kripke. It picks out an object across, a reference picks out an object across possible worlds. A reference is forged in millennia of reinforcement, an accumulation, a hardening, a crystallization of repeated indexings of environmental features is what a reference is. It kind of, they get loaded up through participation. But what happens if you do away with things, as in Lederman and Ross? What happens when you get rid of the supposition of there being relata or objects with properties behind those references? What if the process never bottoms out, as in foundationalism and in all forms of essentialism, but that it is just structures all the way down? In that case, the proper name of H2O, water or aqua, was actually correctly designating or rigidly designating some pattern, which we later discovered had this molecular structure of H2O through an a posteriori necessity. This original referring to water by the word water can be conceived as a tag, an index, like a reference number on a file in a filing cabinet, the content of which is a real pattern. It cannot be nothing. Putnam's we cannot refer to something that is not the case becomes we cannot refer to anything which is not a real pattern. A disturbance happens in the world. Some organisms perceive water and refer to it with some utterance, aqua. That utterance is immediately entangled with the practice of the perceiving organism and perhaps the culture as well that they're engaged with. And the identification of the pattern always implies an action or an actuation on the causal world. Throughout its existence, and even beyond that, the pattern is picked out from all other patterns by the word aqua. Thus, we can track where the water is, how high the tides are, whether or not our laundry is dry, only by reference to this original pattern, which is fixed. We do not need to know that water is H2O to refer to it, just as we do not need to know that the morning and evening stars are the same object in order to refer to Venus whenever we say Hesperus. We were indeed also referring to H2O because both H2O and water and aqua refer to the same pattern, the same repetitive disturbance we encounter in our environments. So Lederman and Ross exploit Daniel Dennett's concept of real pattern to offer, I've already mentioned real pattern, but here it is. They offer us what might be caricatured as a kind of algorithmic compression theory of nature, where whatever is real is that which exhibits some pattern, and thus that which can be reduced. Analogously to how a random string of digits will contain a certain amount of information in algorithmic information theory. Kolmogorov, Chaitin, and this whole line of inquiry around the size of what's in a kind of random string of numbers, and the idea that information is contained in the information contained in a string of symbols is equivalent to the digital size and bits of the algorithm that most efficiently reconstructs it. It provides a rigorous idea of what it means to reduce one theory to another. We can unfold one theory from another. We can use one algorithm to construct another one, and so on. The theory that says, the theory says that the real is just whatever structures allow themselves to be reduced to more economic structures. Those things that can be compressed into models of various kind. That is the real. And actually the compressed form of those models is somehow more real than the uncompressed form. The real is just a kind of universal constructor, a most efficient algorithmic entity that allows us to unfold all the aspects of the real which form the objects of the special sciences. So now let's turn to some critiques of structuralism, because I'm sure some of you are thinking, well, wasn't structuralism over? Are we really coming back to structuralism now? In order to begin to evaluate how well this new structuralism fares, let's look at some kind of critiques of structuralism. Jean Piaget, in his little book on structuralism, suggests that the old, mid-century, 20th century structuralism had a tendency to be totalizing. It's an attempt to explain the particular on the basis of the features of the whole. Piaget notes that, for instance, that the notion of structure is presented as that which requires no auxiliary information. It is itself contained and closed. It is self-contained and closed. It is proposed as an end-all explanation, and yet it seems itself to demand an explanation. Why this structure rather than another? Chomsky will say there is an innate structure in the mind, but Piaget will object, that does not explain the genesis of those biological structures. How did they come into being? So he agrees with the structuralist maxim that the structure achieves a kind of independence from its substrate, but also in a logical sense of being analytic and depending on nothing else, no auxiliary information. In other words, that the structure is closed. And yet, he says, it is open from below and from above. They're open from structures, are open from above in their inaccessible numbers and undecidabilities, incomputable programs, and so forth. The necessary inaccessibility of certain proofs given the most basic of axiomatic systems. They're open from below as well, in the apparent ad hocness of the axioms, the arbitrariness of choosing one set of rules over another, the equivalence of all systems and modalities. One could say here that this is part of a general post-atomistic, post-logical positivist perspective, a perspective where, with Quine, we admit that the rules are underdetermined by empirical evidence. Piaget is sensitive to the apparent arbitrariness of these systems and thus wants to place them within a genetic structure that explains their change in time, their development from simpler structures upward into a hierarchy of subtler abstractions and generalizations, which were, according to Piaget, the character of both the learning individual and the scientific historical knowledge and progress as a whole. Piaget puts it to us quite schematically. We're faced with a trilemma. The structures are either preformed for all eternity, as in a kind of Platonism or essentialism, or they are purely contingent and random, holding to nothing but pure chance, or the third option, his middle way, that there's a give and take between subjectivity and objectivity as a kind of vortex, a kind of process of structurations, a kind of diachronic series of structurations. I'd like to speak about Deleuze as well, and his view of structuralism as summarized in how do we recognize structuralism, which is found in, I think, in Desert Islands and other texts. Deleuze agrees with Piaget on several points, and indeed, one should not consider Deleuze's position anti-structuralist. He first distinguishes the structuralism of Bourbaki, the Nicolas Bourbaki, which is a pen name for this group of authors, French authors writing the post-war math textbooks. So basically axiomatic method kind of stuff. And the structuralism of, the French linguists and social sciences and anthropology and sociology and all that. Lévi-Strauss and Althusser, and he's also thinking of Lacan and Saussure. The mathematical structure, so the mathematical structures, he says, need not be applied to anything. And there's the crux of what follows, because he says that all the other kinds of structuralisms, as soon as a structure is applied, it is misapplied. For Deleuze, structure is a magnificent invention, a creative endeavor, much like that of a creation of a new game, a new form of play. However, he warns, this does not mean that there is nothing at stake. In a sense, Deleuze does not oppose structure so much as expose the structure's limited applicability. The structure always is found ultimately to be wrong, to not quite fit the world. He follows Piaget's line in critiquing the structure's upholding of the primacy of space over time, form over becoming. But the structure is there only to be momentarily occupied, as if by tokens on a board game. The structure provides the grid and the rules within which the play becomes possible. It contains all the possible plays, all the possible different configurations, and gives them consistency, without which the structure would wait statically. Deleuze wants to show the necessity of the structure's animation or application, without which it remains forever sterile. The structure must ultimately stand empirical tests. Deleuze insists that the structure is nothing without this circulation of the symbol, reversals and rearrangements about the narratives that attach to the structure from outside, that order them and dictate how we're supposed to handle them, how we're supposed to read them and interpret them, which configurations come first and which come later, and which have priority, which are emphasized, and so forth. These elements are always circulating, flowing through structures, and the structuralists, he says, somehow do not see them or do not want to highlight them. Deleuze will even be tempted to liken structure with his concept of the virtual, which is quite interesting. Perhaps, this is a quote by Deleuze from that text, perhaps the word virtuality would precisely designate the mode of the structure or the object of theory, on the condition that we eliminate any vagueness about the word. For the virtual has a reality which is proper to it, but which does not merge with any actual reality, any present or past actuality. Here, I argue that Deleuze is falling into a kind of questionable idea about virtuality that comes from Bergson. As I wrote in one of my recent texts on something like an operational virtuality, I prefer Duns Scotus's use of the term virtuality or virtual, where it's a method for naturalizing the divine, a method for taming the chaos around us, creating bridges. Whereas here in Deleuze, following Bergson, we have a wall that's erected between the virtual and the actual, such that they cannot completely communicate all that potential in order to remain unused forever in potentia, must thus never be completely actualized. A true commitment to pure reason that is so nuanced that it becomes unable to act. A Pyrrhonistic position that is also a kind of self-positioning, an affirmation of the one single event of the cosmos, a univocal chant of nature, a single Nietzschean challenge. This absolute estrangement of the virtual and the actual is maintained in order to keep that vitalistic fire alive, so to speak. The potential must never be used up such that novelty and change is always possible. These categories hence must be prevented from being collapsed into the same. They must presuppose each other in a way that makes them irreducible to each other. So Deleuze, we could say that for Deleuze, structures are undermotivated by empirical reality. Does the real call to be reduced to pattern beyond our petty human need to relax the state of emergency, to calm the stresses of living in the wild, living in chaos? And indeed, the defenders of ontic structural realism, Fineman and Ross and others, would accept this, actually. There is no general rule, no all-purpose method for science. There is a certain ad hocness to it, they say. I quote from them from Everything Must Go. The meta-methodological claim is that there is no such thing as a scientific method, by which we mean no particular set of positive rules for reasoning that all and only scientists do or should follow. They abide by a kind of updated sort of verificationism. They adopt the attitude that the current scientific model of the world should be taken with a grain of salt, that the hypotheses declared by current science should be assumed to be incomplete and revisable, while on the other hand, that any hypothesis that is to be taken seriously should rely on, or at least link two other parts, hypotheses, from already established science. The idea here is that one should neither be essentialistic about established science and take it as finished or complete, nor should we be disregarding established science in our understanding of the world. Science is our only traction on the real. It is the only process we know of for clearing our way out of unfounded judgments and claims and opinions, and our evolutionarily evolved and culturally constructed biases. Another quote by Fineman and Ross and Spirit. The epistemic supremacy of science rests on repeated iteration of institutional error filters. So for them, there's nothing sacred about science. It's just an institution. It's just a faulty institution, but that has inbuilt mechanisms for weeding out, its own bad parts. In this way, this new kind of structuralism has found, I think, a way of wriggling its way out from under, some of the old critiques of structuralism. The first, that structures are not mobile, that they lack movement, becoming, process, and therefore that the real world, which obviously is full of temporality, cannot be reduced to such passive, sterile structures. This is, Maimon's critique of Kant. This is Bergson's critique of Einstein. To the first argument, to this argument, ontic structural realism will deny that time or process is fundamental and point to the physics, which we looked at a bit earlier, which seems to clearly show that nothing like the temporal and the mere logical intuitions, which background our intuitive understanding of time, is represented at the fundamental level of description. Fundamental physics is simply the science that applies most generally, applies everywhere. Thus, measurements are meaningful, those measurements which are meaningful everywhere. And it turns out that those measurements see nothing of time. They cannot see time because in the absolute, we should assume there is no such thing. Certainly, intuitive causal time is emergent from the mechanisms science currently understands quite well already, and which form some of the background assumptions for current physics. The other major angle of critique comes from the consideration of what structure hides, its totalizing aspect and its what Derrida calls the center of the structure, the ideology behind the structure, the bias, the anthropocentrism, the phallogocentrism, the logocentrism, the colonialism. To this critique, ontic-structural realism might say, well, this new structuralism is actually opposed to exactly those essentialisms. They're not responding to Derrida and Deleuze, and yet they're also taking a position where science shouldn't be taken seriously or literally. This is because the reducibility of the structures is written into their definition of the real. The real is just that which is reducible. As a pattern, it is that which is reducible, that which is reflectable, or that which can be represented in a pattern, that which can be recast into an equivalence class of different structures. So we should not be too surprised if future science eventually overturns our current assumptions about reality. The whole point of ontologizing structure is to do away with what Derrida called the center of the structure. His famous La Structure, in his famous La Structure, le signe et le jeu, structure, sign, and play, which he presented in 1966 in the US and is said to have inaugurated post-structuralism. He says, that all structures have this center. So he says, ontic-structural realism no longer has this kind of center that Derrida was calling out, this kind of syntax of some invariant form of presence. Derrida names some examples: eidos, arche, telos, energeia, ousia, aletheia. The ontic structuralism does nothing like this, and in fact is constitutively opposed to such explanatory strategies, essentialisms, what they call Neoscholasticism as well. Rather, the emphasis is on an ongoing certification, a vetting, an authentication. A scientific idea must be bona fide. It has to repeatedly be confirmed, generally received by a community of experts who authenticate its worth. It is in this sense that the new structuralism is a materialism, I'd like to say, or we could even say a kind of a dialectical materialism. There's a kind of quietism in their kind of attack on other, analytic philosophers for pulling concepts from here and there, and just invent, saying, the world is made of this, and the world is like this, and the world is like that, or time is fundamental, and or emergence is, supervenience is impossible, or these kinds of things. They're saying something. They're exposing something like the poverty of philosophy. They're saying talk is cheap. Let us experiment. Let us calculate. Calculemos, Let the empirical decide. And science as an institution is just our best, bullshit detector. So we should, basically they're saying armchair philosophers should not be telling the scientists what to do. Where in metaphysicians should not be telling science what to do. In fact, it should be the other way around. In metaphysics, we should be trying to just orient ourselves within this science. The French logician Jean-Yves Girard would argue that this all stinks of a Hilbertian recessivity. The unity requirement echoes axiomatic finitism, the requirement that infinity must be reducible to the finite, and that systems of logic should present us with all the constraints of the real in a nice formal package. Ontic structural realism's connected principles of the primacy of physics and the principle of naturalistic closure, two constraints on their system that act together to order everything else, are much like Hilbert's insistence on consistency. Consistency implies that we cannot prove absurdity from any of the axioms of our system or their derivations, avoiding that it be possible to prove that A equals not A. Girard argues that we must refrain from essentializing structures. The real is not some butcher shop where each answer hangs like a sausage from a rack, he says, in his stunning example of sausage shop realism. He knows that we know that there is not an answer to every question after Gödel. And it seems obvious in hindsight. It now seems absurd to have demanded, as David Hilbert did, that math be proven to be complete, consistent, and decidable from within mathematics itself. As Girard likes to put it, how did we come to believe that we could put everything on the table, including the table? Was this not obviously too much to ask? Again and again, the failures of knowledge are to have taken ourselves too seriously. We impose a one true story, a one true causality, a one true reason, etc. Perhaps we should therefore precisely try to avoid ontologizing structure. And yet the experience of the 20th century in mathematics and physics has shown us that structure need not be totalizing, that more important than structure itself is structural preservation. We have become aware of subtler and subtler modes of structural preservation. We have excavated identities into their relational equivalences. We can mention here the mathematician Steve Awodi with his principle of structuralism. This is from category theory. Isomorphic objects are identical, and how this is extended in Vladimir Vygotsky's univalence axiom, which I also talk about in that article on something like an operational virtuality. He says logical properties are invariant and logical identity is equivalent to equivalence, or equality is equivalent to equivalence, this univalence axiom. With its ever more promiscuous, that is rigorously less discriminating conceptions of identity and equivalence, and we could say even with Deleuze and Guattari, inexact but rigorous conceptions of identity and equivalence. The new structuralisms naturally tend to not be totalizing in the way they used to be. With Vygotsky's work, patterns are even made to comply with the decisions of matter, with the computation that the empirical, in some sense, is the linearity of the underlying system of objective inquiry, the fact that science can't go back, but only forward. The fact that one thing can be represented in another, the fact that we can trace, model, track anything at all is really what is remarkable. Science is just an extension of our ecological perspectivism exploded through technologies. So we may here entertain a question that loops us back to something we discussed earlier. Has science not always been, in some sense, outsourced? Has the movement of science not always been the strange replacement of old structures with new ones in this succession of structures? These realizations obviously challenge the old Laplacian aspiration of science. If we could gather enough data, the future and the past would be clear to us, would be just as present as the present. When physicists claim something like we're getting close to a final theory of everything, they're usually campaigning for the construction of the next accelerator. But science, in its dual principle of revisability and relative explanatory parsimoniousness, was born as a strategy for staying ahead of critique and of doxa. There's no truth at the bottom of this process, one way or another. In fact, the further in we get to it, the notions of truth make less and less sense. As Popper argued, science can only be a negative enterprise. It moves forward by elimination, by creating negative pressures that pull it in various directions. There is no promise that we're slowly filling in all our blind spots such that we will eventually gain perfect Laplacian vision, or that we can even exhaust all there is to know in principle, let alone in practice, no matter how far we get into these levels of abstraction, upwards towards ever more generous accommodations of the real through better approximations of non-pattern, finding the hidden patterns in the non-pattern. So I'd like to end on this. Ironically, it seems to me, structure survives paradigm changes only by nuancing the distinction between pattern and non-pattern. Each reduction, each new theory that subsumes two or more previous theories, is also, in another sense, a discovery of pattern within what was previously thought to not exhibit any, but at the cost of ever more subtle and more delicate conceptions of what it means to be a thing, to be an object, to be related to something else, to be equivalent or not to something else, and so forth. Structures survive the transition by loosening the bonds of identity and equivalence, by diagramming ever more nuanced ways in which one thing is another under a certain light, as well as ways in which a thing is not identical to itself. Thus, semantics, the meaning of our statements, is not grounded in our causally closed compossibility, but rather floats progressively away in an ever receding vanishing point. It is an ever desperate game of catching up with non-pattern. References are a priori contingent, but meanings are a posteriori necessary. They result from a struggle of perception, which leads upward into abstraction, as it were, as it chases an ever receding resolution of non-pattern. Thanks for listening.
Well, that's great. Thank you so much for that really illuminating talk. There's a lot there. So yeah, we're open for questions now. We have about a half an hour. So if you have a question, you can either raise your hand or you can put your question in the chat. Does anybody want to start things off? Well, I guess I have a sort of question. It's a bit general, and it really has to do sort of with what you mentioned in the beginning, and you've been of the talk, and you said that you really wouldn't get or have time to talk about it, and that's the automation of science. And this follows up nicely. This talk follows up nicely on Giuseppe Longo's talk a couple days ago, and basically, based on your conclusion, I'm just kind of curious, like, how do we come back around to the automation of science? And the reason I say based on your conclusion is because it just seems like what you're about to suggest, and maybe this is not correct, is that, machine learning is basically our best pattern detector right now. In other words, it's illuminating, ever more subtle patterns that that the tech that we have up until this point. Look, we have nothing better than this at this point. So I'm wondering if is that the direction you're going in? Is that, or if not, can you sort of map this picture a little bit for us?
Yeah, well, so one of the things I also mentioned in the abstract that I didn't get to is, we don't even have to look at this kind of automated theorem discovery and these kinds of things that are really interesting. I mean, also in the digital humanities, we're doing this. So, we're kind of, we're outsourcing some of our cognitive abilities to these machine learning models, and I don't see why not, really. The question is, whether do we need to continue bypass, the question is, do we need to continue preparing it in a way that's digestible to human minds, in simple, because it does. That's the kind of the problem, is that, like we said, quantum physics is so weird that we can't understand it. It doesn't make any sense for us, and no one knows how, what it's all about. It's just completely, and yet we just have to trust the equations. The equations work perfectly. It doesn't. We don't know what it means or how, but. We're getting to that point where we have to kind of, I think that's what happened, I guess, in the last century. We come to accept this in a certain way, and this is, I think, in part because of computation and how computers have become so ubiquitous. We kind of see this, we feel this substrate independence. We have a feel for it. We don't have to, we don't necessarily think of billiard ball causality anymore, and it took a while for our intuitions to do that. So I'm not sure. I mean, this is I'm not sure whether I'm going to, how much, I could contribute to this field in the book. Another aspect of it is constructor theory, which is, it's different, but it's kind of it's David Deutsch's pet theory, physicist, and also a philosopher of science, Popperian. And he says, from the 80s onward, with the development of quantum computing, it became obvious that there's no real distinction between what a universe can do and what a quantum computer can do, because if it's all just quantum, the only difference is the total energy, how much energy is in the system, but it's the same system, on a certain level. Any quantum system can do the same things. It has the same degrees of freedom. So it kind of means that, the rules of quantum computation are exactly the same as, the rules of the multiverse. They're not necessarily the rules of one universe, which would be could be described as a kind of one program running on this giant universal computer. But yeah, so these intuitions certainly do threaten the kind of traditional idea of science as a kind of process of discovery. And also saying, the question of the Bayesianism, which is also interesting, because it seems that Bayesianism is extremely subjective, and it's about making predictions. It's about making temporal, what's going to happen in the future. And our science is still organized around these principles, and that's why this is why Bayes' theorem, with machine learning became the new kind of the most important equation in statistics, after it had been kind of disused for a very long time, in where in the early for Bayes' theorem is actually Laplace's theorem. It's Laplace who formulated it, and who starts all. So he's also the one thinking about this Laplacian universe, and frequentism took over. The idea of frequentism took over as a way of thinking about statistics for a very long time, until machine learning came, or until Turing had to decipher, German Enigma codes and stuff like that. And then all of a sudden we realized that, Bayesianism is actually great when we have very little information, when we don't know where we're going, and we can slowly approach certain values by using this perspective. So I'm sorry, I'm not.
No, that makes sense. I guess I just wanted to. The one thing I'm thinking about here is given the large enough data set. A lot of people have shown this, that given a large enough data set, you can show a lot of things. You can pretty much show anything to be related or correlated in some specific way. And I'm just thinking about getting the level of organization right. In other words, I'm thinking about the sort of real consequences we have for seeing these patterns. Yeah. And I'm thinking about it like in the biomedical sciences, right? When we start seeing machine learning, anticipating things that are based on, correlations, but it's not causal in any way. And we see this happening all the time in biomedical sciences, in cancer research and so forth. And there's it's sort of hotly debated whether or not we're going to be use machine learning to actually start thinking about, diagnostics and treatment programs and so forth, right? So, at the level of, thinking about the real consequences of using computational systems to actually start doing this kind of work that affects people's lives, and that's one of the things that I worry about.
Yeah. It's definitely disruptive. but like with many technologies, as soon as if it does become effective, it'll be eventually adopted. Vaccines seem to be very invasive, but I think not everyone agrees, but it's these things are eventually I don't know, we'll see. We'll have to wait and see, but
Sure.
Just like anything, really, we have to wait and see. And that's kind of weirdness about science. It's not like we don't know. We just have we just have a best kind of bullshit detector kind of system. It doesn't tell us the truth. It tells us something that's less wrong than most other things.
Yeah, Devar.
Yeah, hello. I would like to add something quickly. I think we have to be a bit careful with the concept of what structure and pattern detection means and so on. So the paper that Anderson wrote, what was it again? The scientific deluge. What's the name of the
data deluge?
The data, the
scientific. Obsolete or something.
So this paper was debunked already many times. So the algorithmic science. How should I say? Algorithms are good in seeing patterns, but we don't know what these patterns means. We don't know what the patterns mean, and the problem is that somebody still needs to contextualize them. So only because we see correlations in something doesn't mean that we have produced knowledge or science or a structure. We just produced something. This can be everything, and you still need somebody to contextualize this. And so we are pretty good in detecting these patterns, and we are good when we are programmed to a certain field, to a certain rule set, to a certain set of rules. Like, for example, cancer detection. Apparently, recently I read something like the algorithmic cancer detection is better than human cancer detection because, of course, the algorithms can see more detail. Or let's just say they see more, let's just say details, whatever. So the point is, they can, and I'm talking about a picture. You make a picture of a melanoma or something like this, a black spot on the skin, and then they are better. Why? Because the rule set is very defined. It's not open. And the same goes, for example, for AlphaGo, which plays better than a human. Why? Because the rule set is defined. Although the limits seem, although the possibilities seem infinite, so to speak, it is not infinite. And they are very good in that. But what they can do is produce new patterns and new structures. And even if they could, you could not know if it's true or not. So, for example, you could think about just as a how to say in English, as a thought experiment. You take all the mathematical operators we know, the plus sign, the minus sign, and whatever, all the operators we know, and you take all kinds of variables, like A, B, C, D, and alpha and beta, and so on. And now you take an algorithm which just tries, in a brute force method, all kinds of possible formulas. Can you imagine what I'm saying? Like, E times E is M times C squared or something like this. And now you take a pattern generator that tries all of those mathematical formulas. You see? Of them.
That's what they're doing. Yeah. Just brute force. Yeah.
Yeah, exactly. And now you project them on nature. And you can be certain that some phenomena, in this infinite space, some phenomena in nature will be mapped by various of these, but still you need somebody to then test if this is true or not. Okay, so what I'm saying is you have to distinguish between what you mean when you say structure or pattern. There are differences.
Yeah. Well, that's why.
And this is something where you need a philosopher or a human, and at least up to now you cannot leave it to calculations, because calculations don't do anything. Calculations are like a hammer. A hammer doesn't do anything. You need a human that uses the tool and puts it in a context.
Yeah, what the authors are saying is that I think it's quite ingenious. They say of course, what you were first of all what you were saying about meaning. We don't know what it. We look at just data. It's just a model. It can create predictions, but it doesn't tell us what it means. Doesn't say whether it's true. It doesn't give us a theory. That's true, but that's the whole thing that's becoming less and less Let's say we're becoming less and less picky about it somehow. Because the further we get into theories, the more we see that there are equivalence class of theories. You know, the ones that are meaningful to us are not necessarily more fundamental than the other ones that are not meaningful to us. So it's all about being, like you said, what is it? There's a kind of instrumentalism about it. Like, what is it for? Like in the case of spotting disease on a human body by looking at skin spots or whatever. That's the purpose. And yeah, when there's a purpose, that's why I'm very kind of pessimistic about AGI, you know, artificial general intelligence, the idea that there wouldn't, like, it's kind of this idea that there could be an intelligence that is not purposive in it, somehow, that it has no specific applications. I think all intelligence is, all intelligence is, human intelligence is not general intelligence. Human intelligence is it's not at all general. It's specific. We have all these tasks that we want to do, and the science that when you say meaning, when something means something, it means something in that sense. So we have all these data. There's all this. The model can be reduced to certain models, certain structures. The AI, the machine learning model, which could have a certain neural net kind of representation, will be equivalent somehow structurally to other models. So you could model other ways on by writing down an equation or something like that. But yeah, there's this kind of the meaning. That's what I meant by a posteriori necessary, because the meaning always comes afterwards. It always comes. We will decide later what it means. The science gives us these a priori contingent references to the real, and then we're stuck, catching up and later on figuring out what it means. But yeah, that's kind of.
Yeah, if I may add something, I'm not sure. I think there's a category mistake here. So water is a pattern. We can call it a pattern, right? But if I call it water, if I'm a, let's say, Neolithic person, so, like let's say 10,000 years ago or something like this, people were interacting with water. So they used something to transport water, and let's say they called it water or something. So they were interacting with this physical structure, let's just say like this. But H2O is a different description. It describes water differently, but the point is that water is still there.
Yeah. See,
the object is there. So the thing was there not a posteriori, but a priori.
Yeah, that's what I'm saying. The science, the water, well,
so it's the point. The idea that it's not contingent.
The idea that it's H2O is a posteriori. That's when we. Well, in a way, it's both, because each time you make an observation, at some point in the scientific process, someone analyzed the molecule and saw that it was H2O, or to fit it into the table of elements or whatever. But that doesn't. So I would talk about this in terms of implicit versus explicit, and I think it's important what you're saying, because and I think we have to not get too carried away, like with by saying everything is just structures. That we can just reduce everything to structures and no longer think about the matter, the empirical world. We need to test everything. These structures need to be tested and vetted, and that's the whole point of having the. When you say a human needs to decide what it means or whatever, that's why we need a scientific community. It's the question becomes then, how do you make sure that the scientific community is not, is working as best as it can, so that it's finding meaning, it's figuring out what this all means somehow. Yeah, I don't know if I answered the question.
Yeah, I mean, what the community does, it transfers a phenomenon, let's say, into a code or into a pattern or a descriptible, operationable pattern, and contextualizes it with other codes and other patterns in order to make it work, so to speak, or to operationalize it, right?
So Jean-Yves Girard, which I mentioned at the end of the talk there, he says, we can't, for example, this Curry-Howard isomorphism, which I talked about when Paul Cockshott was, or whoever, second speaker, what was his name? I can't remember. One of the first two speakers.
Michael.
Sorry?
I think, yeah, anyway, go ahead.
Yeah, so there was this question, I asked a question about, what about the Curry-Howard isomorphism, which is this idea that programs are types and proofs can be understood as programs and propositions are types. This kind of isomorphism, this kind of equivalence between logic, propositional logic and computation and various ways of representing it in category theory and all that. And what about that? Like, wouldn't that count as a kind of dialectical materialism? It's a materialism of the dialectic, let's say, of computation itself. And he said no. Oh, I think it was Paul. He said no. The nature needs to come first. You need the nature first before you have the computation. You need a substrate. And yeah, I think that joins up with this question too. So Jean-Yves Girard, who worked a lot on this question, he says we mustn't essentialize this equation because it masks over the question of implicit versus explicit. And I think it's very important because he stresses, and he's the godfather of linear logic, which has now been found to be equivalent to quantum physics, quantum logic. And it's a logic of resources rather than truths and falsity. It's like what's available, what's possible, so it's about sufficiency rather than necessity. And that seems to be kind of the shape of science as a whole, as a kind of process of inquiry. And he says in that process, you cannot overlook the distinction between implicit and explicit, because certain formulations of a theory, let's say, will be more digestible to human beings, and others will be maybe less digestible, but less efficient. They'll use up more energy. They don't have the same energetic costs. They don't use up the same amount of resources. Ideas and representations of ideas have different representations of one idea will have different energetic or resource related consequences, and therefore they're not equivalent in a way. They're equivalent logically, but they're not equivalent in another way, in a kind of materialist way.
Yeah, but this goes back again to the question that Adam just asked, I think. Today, many mathematical problems or proofs can only be done by a computer, right? And many are being done by a computer. But the problem is no human can reconstruct it anymore and prove it, can so to speak, go after it and say, was it true or not? So we have to believe it, right? Yeah. And so we have some sort of computational, how should I say this, computational guarantee of truth. Okay, if it's computational, it's true. Yeah. And this goes a little bit in this direction that Adam asked earlier. What do we do now? Does this have impact on the real, right? On our real reality, so to speak? That we externalize it to computers, the production of truth. Yeah. So how should I say? There are problems right now. And so to speak, they can only be solved by a computer, and they are being delegated to computers, and then other computers say, okay, it's send computers for algorithms. So other computers then say, okay, that's good enough for me. I'll take your data, I take it in. It's efficient enough, as you just described, with your degree of efficiency. It doesn't have to be true. It has just to be good enough, so to speak. Yeah. So, and here now have a problem because the one computer can spew out something that is good enough, the other computer will take it up, say, oh, it's also good enough for him, he's keeping on processing, and in the end you get to a decision made by a computer which is based on many good enoughs, but is wrong in the end.
But it's wrong,
You
totally,
see, and that's the problem with when we transfer the notion of nature as being made up of structures, and when we conflate it, so to speak, with the structures that computers are producing, then we are equating the potential to be wrong with that which is universally right, which is nature. So in that case, I have a melanome, I have, for example, I don't have one luckily, but I have a melanome, for example, on my skin, and the algorithms say, okay, there is one, there's a dark spot, and then the computers keep on processing it, and in the end, of course, they say, there is one, but there's none, or the other way around, they say there is none, but there is one. So I'm just saying it's we have to be careful with this too quick conflation between the structure in the universe and structure on computers.
Sure. I mean, I think that's what I was trying to do, be very careful about this distinction. That's what I'm trying to do. And I think the authors are. I mean, that's why I'm even talking about it. It's not really my terrain, this whole kind of comes from I come from, Deleuze.
I mean, I'm not criticizing you.
Structuralism, and I read this kind of at first thinking, I'm going to read it, and I was blown away by how subtle the arguments were, and they're very good. I really recommend that everyone take a look at it. It's Anyway, I think it is careful thinking. It's very careful about this distinction, and it's not saying like we should. It's a really kind of rational discourse about, what else are we going to call it? It is structure. We can call it structure or relations or whatever. But this question of, will any object ever kind of be good enough to, be considered some essence or some noumenal real? No, we'll never hold such a real in our hands. We'll only have relations to it, and so and it turns out that the closer you get to the real, the more you get into it, like in those fundamental physics and all that, it just gets weirder and weirder. It doesn't work the way that we think it should work or the way that we relate to it.
Yeah, okay. Can I just follow up quickly on this one more notion? So this is.
I just want to make sure no one else has any other questions, because we are getting to the end of the time.
Oh, yeah, okay.
Okay, go for it.
Okay, sorry. It's important just to clarify that. I think this is a little bit dangerous to say that we don't know things and that we are constantly changing. We know that Newton's law F equals ma, so force equals mass and acceleration, is valid forever, everywhere in the universe.
True. Yeah.
You can go into I don't know if it's valid in a black hole, but in principle, so there is a truth in this, and everything that comes later builds up on that, but then contextualize it a little bit. So it's a little bit dangerous to say that everything's always contingent and in flux. The only thing that is happening is that we are.
But no one said that, right?
The resolution.
That no one said that. No one said that. That's exactly. You're just saying yes. You're saying it's dangerous to say that it's all contingent, and at the same time, it's dangerous to say that it's all fixed. There's dangers in there, but at the same time, that's not what I was saying. I'm trying to be very specific about what it is that. So, the example of Newton, yes, there is some of it. What turns out to be truer in Newton, we only figure it out later. We figure it out after Einstein. We figure out, oh, that was really true. But all of these background assumptions about space being this kind of empty container, and all these background assumptions turned out to be wrong. And yet the form, there's some kind of then Newton's equations become a limiting case of the larger, the kind of relativistic.
Okay, but the container space was not his finding, but a methodological decision to make his findings work.
True. Yeah, it was a methodological assumption,
Yeah.
which he just ran with. That's true. Yeah.
Yeah, but his finding was F equals m times a, you know. So, and this is still true. The only thing that happens then in the next generation is that we are differentiating it deeper. So if you want to transfer Newton's gravitational laws, you can do that with quantum mechanics, and then you put it into a different framework. But the fact that you know, gravitation works in this way is still the same. You see, so the fact is still there, like water is still there. The only thing that changed is that we have a higher resolution on the object and can contextualize it with more phenomena.
Mm-hmm. More
So
general.
in other words,
Yeah, think of it more generally. Yeah, I mean, the same thing comes up also in you know, this kind of all this quantum stuff. You know, which I don't really want to get into, but all this kind of decoherence stuff, which is really, you know, very contradictory as well, because we feel like, you know, the idea that there's all this quantum weirdness in us and around us, and everything's made of it somehow, but we don't see it. You know, things are here. You know, we have objects around us. We deal with like things that are here or there, and actually, all, you know, computation runs on this idea that, you know, that you can flip bits. You know, that you can put a bit there and a bit there, and but somehow this is not really the case, and you know, here and there, like, you know, if we have to take physics, you know, quantum physics literally, then somehow all of this needs to, you know, collapse, or the superposition collapses onto our reality, or, you know, it needs to kind of decohere through environmental effects.
Yeah, but you cannot transfer from this scale to the other scale.
Yeah, exactly. Once your world is decohered, you can't go back, or it would take enormous amounts of energy to.
No, I mean, you cannot scale things that are happening on the nano and micro scale, on the meso scale, or on the macro scale.
I'm not sure.
Yeah, well, this object here, that the cup will not decohere.
No, that's what I'm saying. Yeah, exactly. Once you're decohered, because of the environmental factor, it's already decohered into the environment, which you could say it's then covariant. You know, it's varying along with the other environmental parameters. So it's no longer, you know, it's entangled with the whole world around us. It's because of it's actually the fastest process in nature, decoherence, right? But it's faster than anything else. The fact that you know, that if, you know, there's any energy at all, if you're not in a vacuum or at 0 degrees, at absolute zero, then there's going to be you know, particles decohere, and you have macroscopic reality appearing, you know, just automatically. Yeah, and you can't go back. But it still turns out that, you know, somehow we can't even fathom what exactly this means, but we can have all kinds of interpretations, which is the case, right? Quantum physics has all these scientifically equivalent, you know, interpretations of it that don't really make any difference to the experimental status of the, you know, the reality of the fact that the Schrodinger equation works very well, and all the interpretations are just auxiliary and kind of not really. Yeah. Sorry, that was very abstract for Friday, June. The Friday.
Yeah, this is great. Thank you, Alex, and thanks, Devor, for the conversation. Yeah, well, I think that brings us to the end. So I hope everybody has a good weekend, and we do have another talk tomorrow. David Roden, I believe. So we look forward to seeing you there. And thanks again to Alexander for his great talk.
Thank you. Thank you for being here.
Thanks, everybody.